This section is on the chain rule for multivariable functions. Here's a little warm-up for you. If you like, it can be handy is to draw a tree where you have, and then you have each of the outlets. And when you're doing you follow every branch that leads to you. So that shows I need to do dz dx first. And then I need to do dx du. And then I have one that goes down the y branch, zy and yu. And the same thing for when you do the v. So drawing a tree and following the branches to the root that you need, the bottom that you need, can be a helpful pattern, especially when it jumps up to things with 3 variables. And you'll find when you do it, some things get repeated.
I know. It's the Microsoft Surface. It's a great investment.
These show up in both equations. So you don't need to reinvent the wheel.
In the video, didn't you say you were going to start using W, X, Y, U in the?
I forget what I said.
Oh,
And I need to go back and look at whatever I said. It was brilliant. I remember. I forgot to
yeah.
note of it though.
Instead of writing like, oh wait, I don't know how you do it.
I've done it. Doing like ZX like that and XU.
Yeah.
Right.
Yeah.
I like.
I'm showing it, but like it's handy. You will see this way a lot more often than you will see what I was doing. So it is helpful to know the notation others are using and being able to recognize it when you see it.
True. Makes sense.
It's just the same thing. So if you want to launch those tools, ask for
The secant squared x is the derivative of tangent.
Yeah.
That sounds about right. So we're going dz du. We need that. That's not very bright. Get better color. I did an orange up or red up above. Let's just do that. And now dx du is just v to the -1. And now we need dy du, which is 2uv squared. And derivative with x with respect to v is we bring the power down and lower by power, got negative u over v squared. For a lot of things, you might want to, when you're like using this in reality, you might want to leave it in this form because you may not be sure what parameterizations you want for x and y up here in terms of u and v, and being able to do it like this and change these two things without changing the rest allows you to see what it looks like. But if you want to see it all in terms of u and v, you could then at this point just start substituting in what u and v is, or what x and y is. So dz du, well, I'll start with dz dv because it's at the bottom. X was u over v, so this is 2u over v minus u squared v squared secant squared u over v. Then I got another negative u and a v squared. So, the v squareds cancel out. Look at that. So that'll cancel out that, and I'll have another u, which would make that a positive u cubed. Maybe since those are just coefficients or polynomial, I'll do it like that. And you could do the same thing with dz du. In fact, I can tell you right now, the chain rule shows up on the exam. I think I got a couple different chain rule problems. One doing something where we switch to time, and then another where we do a multi-variable switch like this. But if you're given the time to check your work, you could always technically check it by going back up to the top and substituting in what X and Y were in the beginning. So we had X squared, which is U over V squared. And then I had minus Y, which is U squared V squared. And then I had tangent of U over V. And you could do dz dv without a chain rule at this point. So I prefer writing this like this, U squared V to the -2, because I think I hate the quotient rule. It's tedious. The derivative with that respect to that with respect to B is what we got, negative. And now I've got two things with V in it. I'm going to have a 2U squared V tangent of U over V. Oh, shit. For me to do the chain rule, I'm going to do this. And now I got to do also the one term that has the V or the tangent part. So minus U squared V squared secant squared U over V. And then the derivative of the inside is negative U over V squared. So this last one, this one right here, is that term right there. Then this one is here. And maybe I did something wrong on that first part because, oh shit. I did. That was a fucking fail. That goes like that, which meant that negative UV squared had to hit the 2UV. I didn't use parentheses and I made it so I didn't distribute it correctly. That's a fail. That would change this to negative 2U squared. Over V cubed. And by shit, I would have had submitted the wrong answer on the test. But I took the time to do it the full long way, and I saw that I made an error. Which means I probably need the parentheses right here too, because to be accurate. Does that make sense?
Yep.
Like below this line right here, we did direct substitution. We plugged in X and Y, and then did direct partial derivative with respect to V. Above that was chain rule. Ready for some more?
Yeah.
I know people are writing, but I don't know if they're writing what I was doing, if they're doing their own thing. If you need this, Zach keeps looking up down. I know he's still looking at it. All right, let's put another problem up. Yeah, we're going to find the total derivative. And if I do a little tree, what do I have? W has X, Y, and Z in it. Y is a function of Z X, and Z is a function of X.
Awesome.
Since you all like to know, get a little tip on what the extra credit is on the exam, I'll give you this single tip. It is a word problem from one of the sections in chapter 13. I pulled the extra credit straight from the book. It's an exercise, it is a word problem. I ain't telling you what section. That would be too easy.
Do all the problems in the book, maybe you'll find it.
No, it's narrowed down to chapter 13. I mean, and you know we're not doing Lagrange multipliers because
Pull one over on them.
but it is in there. And like you could theoretically work all the word problems if you had like no life and no other classes and
Yeah, do them all.
no desire to eat or use the restroom or engage with other people.
Sleep.
I like how you associated having no other classes with having no life.
No, it was an extension of no life. It's a subset of no life. Like plenty of people don't have classes, they still have a life. I don't have, well, I guess I do have classes. I don't know if I told you guys this. I don't, for those of you that weren't aware, Lawrence has swayed me into working with you guys next semester over the weekends at Starbucks for DiffyQ and or linear. Even though I am not the instructor, I will do at least one day a weekend in the morning with you guys. Because I want to see you guys succeed.
Yeah, strings your juice.
Awesome, Professor Jones.
Lawrence definitely bribed.
Definitely right. But that's
What?
the question. What did he bribe with?
That is the real question.
He didn't actually bribe me. He asked if I was ever going, I think he asked if I was ever going to teach them. Or teach them sometime soon, because he would like to take the class with me and have the tutoring there. Yeah, he was smooth with it.
Dang, Lawrence.
Yeah, Lawrence. I didn't know you were chill like that, Lawrence.
Bless you. Bless you.
So what are we getting here? dw dx. Well, that's easy. You just drop the x. Plus. Then we'll look at the dw dy.
6x1.
We have 6xy z cubed times dy dx, which is 6x. And then we do dw dz, which is 9xy squared z squared. And then we got 1/2. I think might as well do it in just one step. 1/2 square root of x minus 1. So I could clean that up a little bit. I mean, a little bit shit combines, like right here. Maybe the middle term combines. We could write that instead as 36 x squared yz cubed. But that's really the only one that cleans up, isn't it? I guess I could make this all one fraction. And if we wanted to check our work, we could write W all in terms of X right away. Of course, checking and comparing it with our answer above is very much going to require us to go back and make some substitutions up above. But you could do it. So then you could do, it's not even a partial anymore. There's no partials anywhere. It's just dw dx. And this should match that after substitutions. And if I were to do this, and I'm going to leave this as an exercise for the reader or viewer, I would not multiply this out. I would leave this as is, not multiply it out. Just do chain rule. Hit that one, hit that one, or product rule. Treat these as three functions. W equals A, B, C. A, B, and C, and I would do it that way. A prime B, C plus A, B prime C plus A, B, C prime. That's how I would do it, but I am not necessarily you. Well, I know I'm not you.
So, I know you were showing us like kind of do it with the tree or whatever. That's obviously not how you do it, right? Like, you just get good at it after a while of practice, or like, how do you think about doing, like, when you look at that problem?
If there's enough shit going on, I will use a tree. Like if there was like three variable, like XYZ, and then XYZ was a function of say, rho, phi, and theta, like going from Cartesian to spherical coordinates, I might write it out just to make sure I have it. But in all reality, another way of writing it would be going W equals a function of X, Y is a function of X, Z is a function of X, and just doing it that way, doing the chain rule and knowing I got to keep going inward. So df dx, which is W, maybe I'll say W equals function like that. So just going in one at a time.
Yeah.
And making sure I delve inward. This happened to be a total derivative here. The next problem that we're going to do something that goes to polar. So there's an R and a theta, and I'll show you how I would do this notation with that in a second. As soon as you guys are done writing this down. Good question, Lawrence.
Is it possible to just sub in the Y? So you could also just sub it like you did basically at the bottom, I guess. Just kind of like with your W, just put it.
Yeah,
all
you
Y.
can definitely do this, unless like on the test, your teacher says use the chain rule with the original function. And I don't know
So
about you, but I know lots of teachers that would very much specify that.
So
I'll let you
that's
know
not-
right now, your problems that have the chain rule, I tell you to do it both ways. I think there's two problems on the test that have chain or something like this. And both of them say work it out both ways to verify your answer.
All right, so that's not the original function. I don't understand because
That's the original function.
What's the difference? Oh, no. What I'm saying, no, okay, not that. I'm saying with that original part, not that second part. With that original part, if you just subbed in your values for, like, if you took W and then plug in all those Y and Z values,
I don't
like,
understand.
rewrite that as W equals 3 times, or 3x times 3x squared plus 2 squared times.
Like I did down here.
Oh, is that what you did? Oh. So why is that a different function? I don't understand why that's a different function.
It's a different way of solving it. The problem's
It's
not
just-
different. It's a different way of solving. Here, I'm not, notice I don't have any partial derivatives after making the substitution. This can get really, really, really fucking tedious like this. Especially these are like nice and easy little Y and Z's. But they're not always nice and easy.
Yeah.
Maybe you'll see the point of the derivative or doing the chain rule as is with the next problem.
Yeah. Log.
Mr. Jones?
Yeah.
So
Use it up longer?
no. So I just had a question. So like, as far as the exam would go, for a question like that, if we were able to solve what dw dx would be, do you want us to actually have to go back, like once we have our concluding like equation and actually do like that, like derive it again so we can prove that our work checks out? Or is it okay,
Yes.
like what we just said? So wait, so
The
you do want us
question
to do
says
that?
do it both ways. You'll
Okay. So if
and
the
we'll
question
have a
says do,
review. Don't worry, we'll go over it in class.
It feels like there's
Okay.
so much shit going on. Sorry.
I shouldn't have brought up the test.
Either
Oh,
either way, you
oh,
want to
so,
do it the
Orange.
chain way, and then if
Orange.
you want to do it the other way.
so would you suggest doing the chain rule way first?
Yeah,
Well,
but on the test,
well,
you guys are getting confused because he mentioned it's on the test, and you guys are getting a little antsy about it.
Anxiety.
Yeah, exactly.
yeah, I
You
wish I
just
hadn't
say-
brought up the test. Just
He's just saying that you'll be doing both on the test.
Okay.
But typically, the chain rule is the way to do it, and and then there's a way to just check it.
just check it.
But he'll have you do both on the test. That's all we said.
right. I just did the built-in check on the exam. The chain rule, like doing the chain rule here, I think is quicker.
I don't know there is.
Typically, the way to check it is just really ugly.
If I'm lazy, can I write another form than just like insert?
So rather than doing the tree here, if I'm going after R, I'm going to see I have XR and YR. So I know I need a DX or DT DX, DX DR plus DT DY, DY DR. That's how I would do it without the tree. I don't even write this out. I look at this and go, okay, I got to take the derivative with respect to X. Does X have R in it? Yes.
Then you have to take another, so, okay.
And then when I'm doing,
So, okay.
we'll do DT D theta in a second.
Is that a partial of X with respect to R, or is that a?
It's a partial.
Why in the last one was it just like a regular? Derivative?
Because you notice when we got there, that's a good, excellent question. Why did I use a regular D right here? Because when I got down to it, when I substituted everything in, I could make it just a function of X.
No, I don't mean
I
right there. like,
cannot
back
do
up.
that here. Even
You
if
can
I
go back up.
substitute in R cosine theta and R sine theta, I will have a theta in there, not just an R. So
No,
it's
I
got to
know
be a
he's-
partial.
I know what he's talking about. He's talking about when you go to the bottom of it when say remember.
Like bring up that board.
Bring the previous board real quick.
At the top. See where it says like DW
You have
parcel
probably-
W
it's
parcel of X
Lauren,
plus.
It's because Y and Z are just only functions of X. So you don't, since they're only functions of X, you don't need to.
I could
make
do this.
Since they're not part of a.
DW over DW.
But what's dx dx?
One.
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 So I don't need that.
Okay.
It's a good question. And it had to deal with how the tree was built. Like Brandon was saying, X was already a function of X. I didn't need to write it.
Um,
out.
Do you have a question?
Yeah, so in the equation, the ending, is that a Z or is that a 2 at the end?
I'm pretty sure that's 2.
It's a 2?
It's a two.
Yeah, get
There's
the
no
light.
Z's in this problem. Sorry.
Okay.
Let me make that look a little clearer. How about we just make it a 4 and then there's no confusion.
Yeah.
I changed my answer.
I'm gonna throw off anybody that was already using 2. There, that's a little bit clearly more 2.
People already changed it to 4. Now they have to
It
change
doesn't matter. We take the derivative, it goes away. It's a constant. Y'all calc students, you should know that by now.
It destroys their peace of mind.
There is no peace of mind when you're doing 3-dimensional calculus. Get over that already. That
Are
ship sailed on day 1.
you sure it wasn't day 2? Because day 1 was just introductions.
These are. DC over DU and CC over CT.
So now I'm doing X is a function of theta and Y is a function of theta. So I gotta hit both. Boom, 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 boom. And since I'm smart and I know I don't have to repeat the work, I will copy my parentheses from before. And this problem might actually clean up some if we plugged in it might clean up. because we know sine squared and cosine squared added together equals 1, so it might, but we don't really have time for that here. I guess we'll have to do implicit differentiation tomorrow.
I think this way, like, it's a lot easier to understand.
Yeah.
Because you're doing it like in parts,
In section.
yeah, in sections, and then you're combining it. But
Yeah.
dude, it's,
I mean, it's
depending on like, especially if you have to do,
Yeah, you did. You just try to shorthand some of that. Instead of like actually writing out the entire thing, you just you just put some. The question is, yeah. Is there a part of it that you can't read? Is there?
I'm just like trying to say. Mr.
Oh,
Jones,
so you're getting something-
Yeah.
is that is that symbol between dt over dr and dt over d theta? Is that just the and symbol?
Yeah,
Oh, okay, yeah. I just wanted to make sure.
It's good to have a formula for reference. Like you can also like draw the tree that.
God, that looks shitty. Oh, I made it worse. The ampersand.
That is one fancy ampersand.
Oh,
Now, if you guys really want to challenge yourself on the homework, there's, I'm gonna tab over and show you real quick. Look at 57 in this section. 57 has you switching to cosine theta and sine theta. And if you walk through it, it shows you the polar form of Laplace's equation. This is Laplace's equation. We'll be hitting this at some point. But it'll give you lots of practice in working with something like this. 57 is a good question to toy around with. That is not a hint that it's the extra credit. It is not. But it's a good problem to work on and up your skills. And I know Lawrence is walking out of here thinking that was a direct hint that it's not. That is not the extra credit. But for those of you that like to be challenged, it's a good problem.
No, we don't. And then this is some psychology one. And I actually didn't finish it, so I don't stay and I forgot to do it. And I stayed at home for like 10. I had like only one question I didn't do. That's it. A little bit of sense. So I got out there.
If you guys got any questions, go ahead and ask. It's 8:55. So we don't really have time for another problem.
so you said how you kind of think about it is you just go, like your first thought, I guess, was like, you're gonna take your derivative of the partial of t in respect to x, and then you get to x, and you're kind of like, oh, well, x is a function of r, so then you have to put that in there. Well, and then you go back and start over, and it's kind of like d, or partial of t with respect to y. The y is a function of r, so you kind of like just kind of unravel it. Okay,
Yeah,
like I guess like
it's same way of thinking with the tree as well. If you want, it depends on what you want to use. Whatever makes
so.
your.
What were you talking about earlier? Like switching this to
Brandon,
I guess.
Yeah.
it's-
so if we were just to do this,
No, but we still
like
have to.
the chain rule way, we would just essentially just be plugging in the values of x and y into the original equation, and then doing the chain rule.
That's doing it the regular way. This new way is doing it with partials.
Right. But I'm saying that if we wanted to do it the chain rule way, that's all that would be different, right? We would just plug in what x and y are equal to into the original equation and then just do the chain rule.
You could do it that way, but it will turn out, it will be really ugly.
Right, but
It will give you the same.
okay. And
Yeah.
by the way, how I would
You
do the
could
chain rule.
plug in r cosine theta and r sine theta from the get-go and do it that way. You could.
Yeah, so basically just conceptually, I'm just trying to understand this like in the differences. So the only difference between this method and the chain rule way would be that for the chain for doing it for doing the chain rule, we would essentially just be plugging in the values of x and y into the original equation and then just taking the derivative of that.
Yeah, I mean, it's called a chain rule way, big chain rule, because it really is technically the same way, same thing. It will give you the same answer. Whether you solve the
Why is the
yeah,
notation
by
like common? to write
putting all the
separate
values
than
to make it
write
all.
I can't hear you, Lawrence, because Brandon's closer.
Partial
I said,
Or use
why is
parcels
it like, I
to
guess what
make
you
it
call it,
into,
like common
something like
for them to write the
will give
notation
you
like
the same
that,
answer.
like how you wrote it, let t equals blah, blah, blah with x equals, instead of just writing it all together to begin with.
Like what
Like,
is
why
this
is that
determined?
the standard?
determinist.
Yeah.
This will find.
Does that make sense?
Function. Variable that
First
you
off,
love the
let's,
variable, because in terms of
okay,
another-
so
another variable.
let me plug this in and show you what it looks like if we don't.
And trying to find the relationship of those
Yeah.
variables graphically. This is
So
what's gonna
frictional
help
force
you
is the
at
force
a given
causing
point.
friction. It means that it's gonna be the
Because
force.
because obviously
I didn't do
the derivative
like-
is gonna the derivative
It's
is
the one
gonna
that's
give
causing
you
the
the slope.
frictional
The
force.
slope
Yeah,
at
you wouldn't
that
have-
point.
Doing this, Lawrence, is like, this is like a confusing route. This is the actual what it would be.
That would be
in
like the weight.
percent
That
data.
would be the-
Sometimes it's written like this because it's easier to go do the chain rule
I don't know what else.
and get the answer rather than taking the derivative of this. Looking at this, this can be a little bit overwhelming when I go, well, if I want to do
You know?
deep data,
No, I understand. what you're
this
doing.
is like, fuck, that's a lot to do.
I know where
But
they're
up here,
going.
it's not too bad.
If they just put like, oh, we're doing this, oh, and now we're doing this. Oh, I gotta- Where are you
The
going?
other reasons are, these are we are parameter, remember, we can do a parameter, we're using parameters. So like, we don't know what parameter is gonna be great.
But if you were to ask me.
Did you want that back up?
What would be like the lowest application, like, I don't know if I can tell you what I'm finding.
Yeah, I know. If I had to say, I think this is useful for solving very functions where there's multiple, way more variables than you want. This is because this would make a function like this so much easier to solve than if you just plug everything in and then. That's my.
So-
That's my thought process.
So Lawrence, sometimes we don't know what's the best way to look at something.
I
Like
really
when
don't know.
when we have an equation, sometimes cylindrical's better, spherical's better. Sometimes just doing a simple parameter with respect to time.
Yeah, I'll probably ask him, not that it really matters.
No.
It's just
So
like,
the key here,
I like to
No, I
understand what I'm solving for. You know what I'm saying? Like,
No,
it's an
I
application.
definitely understand that. Yeah.
so this is the original equation, original.
No,
And
yeah, I
then we can
definitely.
try different parameters.
That's-
This happens a lot.
Harder it is to find-
Parameterization is gonna work well.
Yeah.
And so this is a reason why they show it differently. He asked
This is
why they show
definitely,
it. It's motivating you to see that, like,
for example, like,
if you want to plug in
say, like,
parameters, you can do it that way.
Pythagorean theorem compared to this type of math.
All right, thank you.
Hey,
And in fact,
Mr.
doing
Jones.
it this way allows us to change the parameters and test a bunch of different ones.
Hey, Mr. Jones.
Yeah,
Wait, are you gonna go to math lab?
Oh, yeah.
Are you guys having engineering? Okay, for sure. Mr. Jones, so I was just gonna ask, I tried asking, Brandon, but, so what's like an application for this? Like, obviously, like, I know how to like do the math and the calculations, but like, if someone were to ask me like, what the hell I'm solving for, I don't really know if I could really give them an answer. Like, I like to, I
This
guess I
isn't-
kind of want to.
okay, why do we do derivatives at all? Can you, is that
Well,
really a good
obviously,
answer?
Well, I mean,
If
right.
you're
I mean,
learning
obviously,
a
I know that.
tool-
Yeah, I know that a derivative is going to give you the slope, you know, given at a certain point. But the thing is that like,
Okay, my point is this is a tool. we are going to use the tool like partial derivatives and chain rule is you're gonna see it over the rest of the semester and what we're using it for. If you want to see like specific examples, let's see. Let's go for a word problem up here that uses it. Ohm's law, voltage. Problem 36 gives you an example. There are uses for it. Right now, you're just learning the tools. The same reason you learned most of the shit you do in mathematics. You're learning a tool. The applications come in.
That's what.
But we gotta learn the tool first. Like if I give you a new power tool, like a hammer's too simple. But if I give you a new tool and tell you go use this, you need to learn how to use the tool first before you go use it.
Right.
I'm not in static. And no, I haven't not been in static.
But you'll see this a lot through the rest of the semester. You'll see why we use partials. Starting with the next section, 13.6, gradients. We use these chain rule and partial derivatives there, and you will see applications for it.
Okay. Yeah, because because honestly, like this, I could see the usefulness of using this method because it's a lot simpler breaking down like the derivation into like components and like into pieces and then putting it together versus if you had something like, if you had something like a full equation and you were going to do it the chain rule way, obviously you're going to arrive at the same point, but it's obviously going to be very ugly.
Right.
Yeah. And I feel like there'd be a lot more room for error. So I like this. I like this technique. Honestly,
For the next section, when we do gradients, the gradient shows us what direction, like on a surface, has the steepest slope at any given point. You could be at any point, like on a mountain range. If you had an equation for the mountain range, let's say,
okay.
It's three-dimensional space. At any point, if you had the equation, you could figure out what way's the steepest slope and what the slope is. So it's a way of generating the slope in any direction shortly, but we need to get the tools first.
Okay. I mean, I appreciate these fucking alarms.
No problem.
I should, no, seriously, thank you. I appreciate you explaining that for sure. But yeah, and I actually have a crack at that, because I don't know, I'm kind of a person that like when I learn how to do something in math, like I want to know like how I can apply this.
I do
can
too.
apply it.
I am the same way. I appreciate that.
Yeah.
If you, whenever you're doing something like that, you can always glance through word problem, like the problems in the section, and you'll see examples like Ohm's law shows up right here. This is doing something with a triangle. So rates of change on a triangle, related to like how the angle's changing. We have a triangle. As the angle changes on a triangle, how is that affecting the changes on the lengths and stuff like that? So there are different uses, but this is a tool that can be used in a lot of ways. So learning how to use the tool is a starting spot.
Okay. I'll see. Well, hey, Mr. Jones, really appreciate it. Yeah, thank you.
Is this for incurring interest on a balance or is this
You have
for
an answer,
incurring
good?
interest on a debt?
You too.